station, this is the Tug. Final approach checklist is green, requesting permission to dock.
We are going to the moon, and we are going there to stay this time.
The first trillionaire in the world is going to be the person who first mines asteroids.
Question: if launching a single kilogram from Earth costs a small fortune, how do we ever reach Mars affordably? You clicked for NASA's moon mining plan. Stay here because we're going to show how turning lunar ice into water, oxygen, and fuel flips the economics of deep space. Right now, every mission drags Earth's gravity tax. In the next minutes, we'll map the problem, why it worsens with scale, and how ISRU and NASA's current prospecting missions turn the moon from a destination into a depot. The payoff: you'll see the exact bottleneck this solves and why it matters for the next era of exploration. The number that kills Mars' dreams isn't distance. It's dollars per kilogram fighting Earth's gravity. Every item you add to a mission has to climb out of a 9.8 meters per square second gravity well, and the rocket equation punishes you for it. You pay a steep penalty because thrust must accelerate not only the payload, but the tanks, engines, structure, and a mountain of propellant. Then you add more propellant to move the propellant you already added. That loop keeps compounding until a reasonable payload becomes a skyscraper of fuel. Now look at how that plays out when you try to send people, not just probes. On paper, a Mars mission looks clean. One transfer stage, one habitat, one lander, one ascent vehicle. In practice, mass multiplies like nesting dolls. A crew habitat needs power, thermal control, life support spares, and micrometeoroid shielding. Long cruise times push you toward radiation protection, which adds more kilograms. Surface supplies balloon with food, water, tools, and a pressurized rover. The ascent stage demands its own propellant reserves to get back off Mars, and those reserves must be launched and protected months in advance. Each layer forces larger tanks and stronger structures, which need even more propellant. That's why launch vehicles split into stages. You drop empty weight to keep accelerating the rest. Even then, payload fractions bite hard. Historical super heavy rockets like Saturn V devoted the overwhelming majority of liftoff mass to propellant while delivering only a sliver to translunar trajectories. Modern heavy lift follows the same physics, even with better engines and materials. When you ask for more delta V, say, low Earth orbit to a translunar injection, the fraction left for useful cargo shrinks again, and the bill climbs. The ledger has other silent taxes. Cryogenic propellants boil off, keeping liquid hydrogen and liquid oxygen cold during long waits on the pad, and in space needs power and insulation, or you lose mass you paid to launch. Margins stack up because engineers protect against uncertainties. Extra fuel, stronger structures, wider safety factors. The poster shows a sleek ship, the spreadsheet shows tank farms. Here's a quick intuition for the math. You add fuel to push fuel, because each kilogram of propellant brings its own penalty. The rocket equation is exponential, so doubling your required change in velocity doesn't double the fuel. It can multiply it several times depending on engine efficiency. That's why refueling in orbit looks attractive. Break the mission into legs, top up between burns, and your vehicle can be smaller at liftoff. But now you need propellant depots, cryogenic storage, and reliable delivery flights. You've moved the problem from one giant mountain to a series of smaller, but still expensive hills. There's also a cost beyond money. Heavy launches inject black carbon into the upper atmosphere where it lingers and absorbs sunlight. Rocket plumes produce nitrogen oxides that participate in ozone chemistry. The acoustic environment near pads is brutal, demanding water deluge systems and reinforced infrastructure. Scaling to dozens of heavy missions per campaign isn't free for the air, the coastlines, or the communities near launch sites. As cadence increases, those impacts stack with the financial ones. So why does $10,000 per kilogram show up in headlines? Because when you total manufacturing, operations, range costs, reusability limits, and that exponential propellant burden, each delivered kilogram carries a deep gravity tax. 4 multi-mission Mars plans, Earth-only logistics spiral into fleets of launches, years of staging, and budgets that bend under the mass of their own fuel. There is a place, though, with 1/6 the gravity, no atmosphere, and ice locked in permanent shadow. It holds the ingredient deep space needs most: water that can become oxygen, hydrogen, and life support. If hauling everything from Earth breaks the bank, the next question is obvious. Where do we get the mass that mass needs? The moon's darkest craters may be the brightest line on the budget for reaching Mars. If Earth's gravity acts like a toll booth, in situ resource utilization flips the route. You don't haul everything from home. You make mass where gravity is gentle and air is absent. Water ice is the keystone because it does 3 jobs. It keeps crews alive as drinking water and humidity control. It becomes breathable oxygen. And, with the right processing, it turns into propellant. One resource supports habitat, life support, and engines, and that consolidation trims launch counts right where they hurt most. Finding that water is the first hard step. The South Polar regions hide cold traps at temperatures so low that volatiles stay locked for geologic timescales, but the distribution isn't smooth. Ice can be mixed like dirty snow and regolith, or baked into grains as frost films, or concentrated in pockets a drill might miss by meters. Sunlight barely grazes the crater floors. The terrain is jagged, slopes are treacherous, and temperatures in permanent shadow can sink below what most electronics tolerate. Lunar dust is sharp and clingy, grinding seals and coating radiators. Any miner, even a robotic one, needs to operate through deep cold, abrasive grit, and limited power. Once you can access water-bearing material, the chemistry is straightforward, but the engineering isn't. Electrolysis uses electricity to split H2O into oxygen and hydrogen. If you chill and store them, you've made LOX and LH2, the same high-performance propellants that powered Saturn-era upper stages and many modern engines. Even if a mission prefers methane fuel for handling, oxygen is still the mass hog in most mixtures. Sourcing oxidizer from the moon lets you launch far less from Earth, then top off in cislunar space. In other words, you cut the heaviest part of your propellant bill without changing destination. NASA is fielding prospectors to make the map before the mine. Prime 1 aims to test a small drill and a mass spectrometer on the surface, sampling subsurface volatiles and proving the plumbing of extraction and analysis in lunar conditions. The larger step is Viper, a rover planned for the South Pole with instruments to identify how water appears, granular ice, bound in minerals or frost, and how accessible it is to hardware. Its traverse routes target regions with different illumination and temperatures, stitching together a ground truth map that remote sensing alone can't provide. That data decides where an actual pilot plant should land and what tools it must carry. Think of the supply chain as rungs on a ladder. First, lightweight scouts sniff out hydrogen-rich soil and assess trafficability. Next, a pilot plant heats and processes regolith, condenses vapor, and measures throughput per day. Power comes from solar arrays perched on high ridges with near-constant light, feeding cables into shadow or beamed by microwaves to small receivers. The extracted water circulates to electrolyzers and then into cryocoolers, filling insulated tanks that can sit for weeks. A tanker stage ferries propellant to a fuel depot parked in low lunar orbit or near an Earth-Moon Lagrange point, where transfer vehicles dock, refuel, and go. Yields and energy are the levers. If a cubic meter of cold-trapped soil gives tens of kilograms of water, a field unit must process many cubic meters per day to matter. Extraction methods can need on the order of megajoules per kilogram to heat, sublimate, and purify water from mixed regolith, so power budgets drive plant size. A Mars transfer stage may demand hundreds of tons of propellant across a campaign. That translates into tens of tons of water per month from the surface when you factor in electrolyzer efficiency, storage losses, and depot boil-off management. NASA's timelines point to prospecting now, pilot operations next, and then scale production. As that matures, propellant sourced off Earth starts shaving launch manifests. Gold doesn't run engines or close life support loops here, water does. When oxidizer comes from the moon, the count of heavy launches for a Mars mission slides from many dozens toward a steady cadence supported by a working depot. With prospectors rolling and drills biting into shadowed soil, the moon stops being a flagging footprints goal and starts acting like infrastructure. The cheapest kilogram to Mars isn't launched, it's manufactured off Earth. The moon offers the first factory floor, low gravity, no air, and access to water that becomes oxygen, hydrogen, and closed-loop life support. That shifts cost, cadence, and risk away from Earth's gravity well and into a reusable supply chain. Track NASA's prospectors like Viper as key milestones, not side quests. They decide where we set up hardware, how much power we need, and what throughput actually looks like. If you want interplanetary travel, follow the supply chain.
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.